Okay. So, this is the last tutorial class. The problems are based on the Riemann integration and related topics. So, first problem is, let f is a mapping from or a function from a b to r be a bounded function suppose that there is a partition P of the interval a b such that the LP f is equal to UPF. The lower sum of the function f over the partition P is the same as the upper sum of the function f over the partition P. Then show that the function f is a constant function. So, what is the upper sum and lower sum? The upper sum, when you partition the interval a b into sub intervals, and this is the function f which is continuous defined over this interval a b, then we get this the sub intervals where the lower values and upper values, say small m I and capital M I, then upper sum of the function f over the partition P or is nothing but summation of m I into mod of x I minus x I minus 1 and I is say 1 to n, it is a partition for them. Similarly, the lower sum m I is replaced by the small m I, we get this. So, this given the function f is a bounded function and there is some partition for which the lower and upper sum are the same. Therefore, we have to show that f is a constant. In that case, the f must be a constant function. So, let P be the given partition as x naught which is equal to a less than x 1 less than x 2 less than say x n which is b. This is a partition of P interval a b, partition of. Let m I or m r, let us be m r is the supremum of the function f x when the x belongs to the interval x r minus 1 x r when r is 1 to n, and small m r is the infimum of the value of the function f x when x belongs to the interval x r minus 1 x r, means sub intervals when r is 1 to n. So, upper sum of the function f over the partition P is nothing but m 1 x 1 minus a plus m 2 x 2 minus x 1 and so on plus m n x b minus x n minus 1, and the lower sum is equal to small m 1 into x 1 minus a plus a small m 2 into x 2 minus x 1 and so on, and small m n b minus x n minus 1. So, this is the lower and upper sum. It is given the lower and upper sum is the same, given that lower sum and the upper sum is the same over the partition P. So, we get from here is x 1 minus a into m 1 minus small m 1 plus x 2 minus x 1 into m 2 minus small m 2 and so on, plus b minus x n minus 1 m n minus small m n is 0. But m 1 m I is a upper value maximum value of the function over the subintervals, and m 1 is the smallest value. So, m 1 minus m 1 and this x 1 minus a, these are the partition x 1, x 2, x n. Since these are x 1 minus a is greater than 0, x 2 minus x 1 is also strictly greater than 0 and so on, all these b minus x n minus 1 is also greater than 0. So, when the sum is 0 implies that each of m I must be equal to small m I for each I. It means the function f has a maximum value and the minimum value same throughout the any subinterval. So, f is a constant function. F is a constant function. That is what we wanted to show it. Okay. Now, next example is the function f x defined as 1 if x is not equal to 1 and 0 if x is equal to 1. Is Riemann integrable, is the function Riemann integrable over the interval 0 to 2. Okay. Now, the solution of this is so what is given is the function f x is given like this over the interval 0 to 2. The function when x is not equal to 1, it is 1. So, the function is like this, and here this is like this, and when x equal to 1, this is 0. So, this is x equal to 1, it is 0. It means function has a discontinuity at the point x is equal to 1. Function is not defined at x equal to, it has a sudden jump at x equal to 1. Okay. So, it is discontinuous at this point. Now, if P is a partition, let P be the partition of the 0 1 interval 0 2 interval, then the obviously the upper sum of the function f over this partition, that is k equal to 1 to n m k x k minus x k minus 1 is 2. Why? This P is a partition. So, partition P is equal to x naught, which is equal to 0, less than x 1, less than x 2, less than x n, which is equal to 2. Now, in between there is a point 1 also. So, we can have the partition like this. Now, m k over any subinterval when you partition it, the upper value of the function or the supremum value of the function over this partition will always be 1, because when x is not equal to 1, the value is coming to be 1, and here also the value is coming to 1 except x equal to 1. But when you take any interval, any subinterval that even include the x equal to 1, the points are such where the function has a value 1. So, upper sum maximum value m k will always be 1, and the sum of these sub partition is nothing but 2. Therefore, the upper sum will always be 2. However, the lower sum P f is strictly less than 2. Why is it strictly less than 2? Because there is a subinterval. Say I take the subinterval 0 to 1 is this. I choose the subinterval like this, just a 1 minus epsilon 1 plus epsilon, having the length say 2 epsilon. Now, in this subinterval, at least this point is 0, at least this point is 0. So, lower sum will be 0 in that case, because the minimum value is there. So, 2 epsilon length is subtracted from here. So, this will be 2 minus 2 epsilon or 2 minus epsilon. Therefore, this will be, that is, we can say it is 2 minus epsilon or 2 minus, if we take this epsilon by 2, 2 minus. So, it is strictly less than 2. So, this is clear from here. Now, let us choose the, we wanted this integral whether it is Riemann integrable or not. So, let us pick up the partition. Suppose P is this partition, which is value x naught is 1, then 1 minus epsilon, then 1 plus epsilon, and then 2. It means we are partitioning this 0 to 2 as x naught, then you are taking 1 minus epsilon as x 1, then x 2 1 plus epsilon and say x 3. So, 1 is the point somewhere lying here, this is 1. Okay. So, let us compute the upper sum and the lower sum. So, upper sum will always be, upper sum of this any over any partition will always be 2, but what about the lower sum? Lower sum of this is over the partition with respect to this say p epsilon. So, I take the p epsilon partition, the partition is, so lower sum is in between 0 to 1 minus epsilon, the value of the function is 1. So, it will be 1 into 1 minus epsilon by 3 minus 0. Then over this interval it is 0, lower sum is 0. So, it is 0 times of 1 plus epsilon by 3 minus 1 minus epsilon by 3, and over this interval again it is 1 and then 2 minus 1 plus epsilon by 3. So, that is the we get, and finally, what we are getting is this is 0, this is 1 minus epsilon by 3 and then plus 2. So, 3 minus that is 1, this is 2 1. So, 1 minus. So, overall this sum comes out to be 2 minus 2 epsilon by 3. So, upper sum is this, lower sum of this. Therefore, what is the difference? P f minus lower p epsilon minus lower p epsilon f, this is also p epsilon, is nothing but 2 epsilon by 3, which is strictly less than epsilon, and this is the next sufficient conditions for a function f to be Riemann integrable, that if for a given epsilon, if certain epsilon, the upper sum minus lower sum is strictly less than epsilon, then the function must be Riemann integrable. So, this shows f is Riemann integrable. Okay. So, that is the next. Let 0 less than a less than b and f x is defined as 1 if x belongs to the closed interval a b intersection q, where q is the rational number, set of rational points, if x belongs to interval a b is irrational points. So, q is set of rational number in the interval say a b. In rational points, we can say points in the interval a b. Now, find the upper and lower sum. Riemann's, find the upper and lower sum and Riemann integral and upper and lower Riemann integrals of the function f x over the interval a b. Okay, so, let us see the solution. So, function is given to be 1 when x is the rational numbers. In fact, the intersection of a b means set of all rational number in the interval a b. So, at the rational point in the interval a b, the function attains the value 1, while for irrational point the function attains the value 0. So, since rational and irrational points are dense in R, it means whatever the subinterval you choose, there will be infinitely many rational point as well as infinitely many irrational point are available for this. It means the function will attain both the values 1 and 0 over any subintervals. Okay. So, let us take a partitioning. Let P be a partition of the interval a b. Suppose this partition is, say, a is x 1 less than x 2 and less than, say, x n, which is b. Okay. Then what will be the infimum and value and the supremum value of the function? Then infimum of the function f x when x belongs to the interval x I minus this and x I plus 1, when I values from 1 to infinity, I is equal to 1 to n and so on. What is the infimum value? Now, the function attains the value 0 as well as 1. When x is irrational, the value will be 0. When x is rational, the value. So, f x will have 0 and 1 both. So, infimum is 0 and the supremum will be 1. Supremum will be 1. 1, 2, 3 is 1. So, that is therefore, the lower sum of the function will be 0 and upper sum of the function over the partition P will be equal to what? The maximum value will be 1, the total length of the interval is b minus a. So, it will be the b minus a. Okay. Now, hence, the lower Riemann integral a f x dx, this will be equal to supremum value of the lower sum of all the partition over partition, that is 0, and upper Riemann integral of this function is the infimum value of the upper sum over the partition, and that is b minus a. So, this is the answer for it. Okay. Clear? The next example is 6. Example, say 4. Let 0 less than a less than b and f x is defined as 0 if x belongs to the rational, x is the rational number over the interval a b, and x if x is in the interval a b, what it is, irrational points, irrational. Then find the upper and lower Riemann integrals of the function f x over the closed interval a b, and conclude whether whether f x is Riemann integrable. So, this problem is parallel to our previous one, a slightly difference is there because we are taking x. So, earlier when we are taking something constant etc., it was not coming to be a Riemann integrable, but in this case you will see it comes out to be a Riemann integrable function. So, let P be the partition of this, say A is x1 less than x2 less than xn be a partition of the closed interval AB. Then infimum value will be infimum of f x over this partition P. If I take the infimum of P, then this is 0 because of the one point, and the supremum of the over partition P, that will come out to be what? X I plus 1. Why it is so? Because this is our interval A B. When we are taking the partition of this thing and so on. So, suppose I choose this partition over this x 1 to x 2. Okay. The function attains both the value 0 as well as x. So, x is the largest value at this point, otherwise at this point it is 0. Similarly, for this interval it is the largest value and at this point it is 0. So, it has a value 0 and then rational and irrational, and among rational irrational point it has a value x 2 and then x 1, but x 2 is greater than x 1. So, therefore, over each sub intervals supremum over this interval x I into x I plus 1 is x I, where this infimum also you can take x I to x I plus 1. So, this is 0, this is x I plus 1. Therefore, the lower sum of this will always be 0, while the upper sum of this is nothing but what? The first is x naught x 1. So, it is equal to x 2 minus x 1 and then continue this. So, we get x I minus x I minus 1 into x I, and last is x n minus 1 because of this. So, this is nothing but the upper sum of the P, and the function f is identically x. So, you can say h is identically x function, where the h is the a b to r. In fact, it looks like that this is the functional value. So, f x equal to h. When h is x, so the functional value is x 2 over the interval x 2 to x 1 over x I minus 1, the maximum value is x I, and like this. So, it is a function x. Therefore, this mapping upper sum will be, so basically what we get is that since h x is a continuous function, where the h x is equal to x and is Riemann integrable. So, h x is Riemann integrable function. Every continuous function over the closed interval is Riemann integrable, and the upper Riemann integral sum of this h x dx is equal to what? The infimum of upper sum of p h, and that is equal to b square minus a square. Okay, upper sum. And then for the lower sum also we get this thing. So, Riemann f is Riemann h is Riemann integrable function, h is continuous, h is Riemann integrable, and the upper sum is this. Now, when infimum is taken over all partition, the lower sum of this f x dx, not h x, this is the supremum of L P f, which is 0. So, upper integral of f x dx, this is equal to infimum of u p f, and that will be equal to b square minus a square. Okay. But upper and lower sum differs, therefore, f is not Riemann integrable. F is not H is Riemann integrable because the behavior is this one. Okay. So, we are getting this one. Now, let us take the last one result, that is so that function f, the function f defined as f x is 1 by 2 to the power n, when x is lying between 1 by 2 n plus 1 to 1 by 2 n and 0 otherwise x is 0. Okay. X is 0. So, when you say is Riemann integrable, is integrable, although it has an infinite number of points discrete, although it has infinite number of point of discontinuities. The reason is this, because when we open this f x, the f x is coming to be 1 when this lying this equal to half when x lying between 1 by 2 square less than or equal to half, and continue 1 by 2 n minus 1 when x lying between 1 by 2 n less than equal to 2 n minus 1 and 0 when x is 0. So, f is bounded and increasing function, therefore, monotonic increasing, therefore, f is Riemann integrable. Okay. So, that is all. Thank you.